My name is Riba Jin, and I'm a researcher from NICT in Tokyo, Japan. Today, my topic is highly efficient entanglement swapping for long-distance quantum communication. So I have several collaborators from NICT and UEC. So in this talk, firstly, I will talk about the motivation and the introduction. In the introduction part, I will talk about our entangled source and our single photon superconducting nanowire single photon detectors. And then I will talk about experiment and the result. In the result part, I will talk about our four-fold hormonal interference and teleportation, and also entanglement swapping. Finally is a discussion and a conclusion. Now this is our motivation. As we know, repeaters play an important role in the classical communication. Now we consider the scenario of quantum repeaters. So if we want to distribute entangled photons between Alice and Bob, traditionally, so the distance is limited to 500 kilometers due to the loss in the fibers. So this problem can be solved by using the quantum repeater scheme. Here we use two entangled sources, and we make a Bell state measurement here, and then the distance between Alice and Bob can be doubled. Such a scheme can be expanded to multi-quantum repeaters, and finally, it can be used for a global quantum communication network. Here we combine with the quantum memory. So we know the global quantum communication requires quantum repeaters, and the quantum repeaters requires very good entanglement swappings. So this is our motivation, and we will discuss the entanglement swapping in this talk. So firstly is a previous result on entanglement swapping. So the first entanglement swapping experiment was demonstrated at 800 nanometer wavelengths. And later, many entanglement swapping experiments was also demonstrated at telecom wavelengths. Here are several examples. So they use different crystals and at telecom wavelengths. And we focus on the count rate here. We can see the count rate in the previous experiment is very low, less than 0.1 count per second. So if the count rate is very low, to acquire reliable data, we need to accumulate for a long time. So this is a big obstacle for the future quantum communications. So there are mainly two reasons for this low count rate. One is the low efficient source, and another is the low efficiency detectors. So in our case, in our experiment, we will use a very highly efficient source and highly efficient detectors. Here is our source. We use the QCrypt crystal from a parametric down conversion process to generate the photon source. So the QCrypt crystal satisfies the group velocity matching condition at 1584 nanometer wavelengths. So under such a group velocity matching condition, the pump envelope function is like this. It is 45 degrees to this direction, and the phase matching function is 45 degrees to this direction. Therefore, we can achieve a round shape in the joint spectral distribution. So here, we can see this is a round shape. So there is no spectral correlation between the signal and analog photons. So the spectral purity is very high. Therefore, we don't need to use very narrow band pass filters to increase the purity. Not only the purity is very high, but also the tunability is very wide. Here this is the simulation data for the joint spectral distribution from 1500 nanometer wavelengths to 1700 nanometer wavelengths. We can see in all the wavelengths, it can keep a round shape. And we also experimentally measured the data. We can see the experimental data corresponds well with our simulation data. Then such a spectral purity is very important for the multiphoton interference. Here we use 2 of the same PPKDB crystal and make a 4-fold hormonal interference. And we got a very high visibility, about 85%, without using any bandpass filter, because the intrinsic spectral purity is already very high. Then we update the single photon source to an entangled photon source, use a Sagnac interferometer. So we put the PPKDB crystal in the Sagnac loop. Here we have the clockwise pump and the counterclockwise pump. And this is a model of our experiment setup. We have the H photons from a counterclockwise pump here, and the H photons from the clockwise pump here. And the V photons was swapped at the dual wavelength PBS here. And we also make a simulation for the Sagnac loop. So this simulation is very helpful to achieve a good alignment in the experiment. Next, I would like to introduce our detectors. It is superconducting nanowire single photon detectors. So the efficiency is very high. It is over 70%, and with dark count rate about 1 kilocount per second. And the recovery time is 40 nanoseconds, and the spectral range is very wide. It's over 200 nanometer, and can achieve very high efficiency. So with these high efficiency detectors, we measured a single photon source, and we got a single count of 5 MeV and a coincident count of 1 MeV at 400 milliwatt pump. This is the highest ever reported at a telecom wavelength. Then we use the high efficiency detector to measure our entangled photon source. Here we use a beam width of 45 micrometer and with an overall efficiency of 0.2. And we got a coincidence of 40 count per second at a 10 milliwatt pump. And all the visibilities is over 98% for different bases. So the main advantage of our photon entangled source is it is very stable because we use a Sagnac loop. And also the intrinsic spectral purity is very high. As shown here, this is the joint spectral amplitude, and this is the intensity. So the traditional source, the purity is only 0.16, but in our case, we can achieve 0.82. Okay, next we use 2 of the Sagnac source, PPKDB Sagnac source, to do the entanglement swapping experiment. Here we use Mila 900 as the pump source. We use 792 nanometer and 2 picosecond. So the pump is split as 2, pumped this Sagnac source and this Sagnac source. And we use 80 milliwatt for source 1 and 85 milliwatt for source 2. And the average photon numbers per pulse is around 0.1. Here we use the setup A to test the polarization, and use figure B to demonstrate the 4-fold hormonal interference, and also use this to demonstrate the teleportation. And we use figure C to demonstrate the entanglement swapping. So in B here we use a fiber beam splitter, and here we use a fiber beam splitter and a fiber polarization beam splitter. Okay, this is our setup. The laser comes here, and it pumps one Sagnac source here and another Sagnac source here. This is our crystal. The first crystal was 31.5 degrees centigrade, and the second crystal is about 40 degrees centigrade. And we can see the Sagnac loop is very compact. It is only 9 centimeter by 9 centimeter here. And all the photons is coupled into single mode fiber. this is our the measured result of our polarization correlation measurement. So with a pump power of 80 milliwatt for source 1 and 85 milliwatt for source 2, and we accumulated in 1 second, and we got a coincident count of 150 kilocount per second. And the net visibility is around 97%, and the raw visibility around 87%. So the difference was mainly caused by the multiplier emission. Then we confirmed this is a plus-minus state by theoretical calculation. Next, we show the four-fold Hong-Mandel interference. This is a model of our setup. And without using bandpass filter, we achieved a raw visibility of 67% and a net visibility of 78%. Then we add 2 bandpass filters here, and we got a net visibility of 85%. And then we add 4 bandpass filters here, and we got a visibility of raw visibility of 87%. We can compare these 3 results, and we checked the 4-fold coincidence count rate can achieve over 100 count per second in our experiment with 2 bandpass filter here. Then I want to talk about how did we subtract the background. So we know the background was mainly contributed by the multiphoton emission from each entangled source. So we can subtract the background like this. So firstly, we block channel 1 and measure a 4-fold coincidence. And then we block channel, we first block channel 1 and then block channel 4 and measure a coincidence. Then the summary of these two coincidences is the background count. So next I want to talk about the visibility and the spectral purity. We know from these references, we know the visibility in the 4-fold Hong-Mandel interference is determined by the purity of each source. If we want to achieve high visibility, we must to improve the purity as high as possible. That's why we introduced a coarse bandpass filter in our experiment, not a narrow bandpass filter. We can see the bandwidth of our bandpass filter is around 2.1 nanometer, and the bandwidth of our source is only 1.1 nanometer. Therefore, we call this is a coarse bandpass filter. And in theory, we consider with very small loss, we can improve the purity from 0.82 to 0.99 by using a bandpass filter to cut the side lobes here. Then we move on to the teleportation part. Firstly, we talk about the bias data analyzer. So, So firstly, we use a beam splitter as a bias data analyzer. So only one of the 4 bias states can be detected at the output. Therefore, if we have a coincidence between the port at the output port, we know the plus-minus state was detected. And also we consider the second kind of bias data analyzer. Here we use a combination of a beam splitter and a polarization beam splitter. In this case, if we have a coincidence count here, we know the plus state was detected. Next, I talk about the principle of teleportation. Here we use source 2 as an entangled source. And we use source 1, use channel 1 as the initial state, and channel 2 as a herald. And by the calculation, by this long calculation, we know finally the state on channel 1 will be teleported to channel 3. Here we give 2 examples. If we have channel 2 originally in V polarization, then it will have the correlated photons in channel 1 in H polarization. Then with Bell slit measurement, it will select the correlated photons also in H polarization. Now, if the polarizer 3 here with 0 degree, the photons are correlated, so the coincidence can't exist, and there will be no Hohmann dip. In contrast, if the theta 3 here is 90 degree, there will be no correlated photons. And in this case, there will be a Hohmann dip. Similarly, if the photons in channel 2 is in a H plus V state, in this case, if the theta 3 is at 45 degree, there will be a Hohmann dip. And if it is at 135 degree, there will be no Hohmann dip. So here is the result. If we have the polarizer 2, polarizer 3 with the same angle, there will be a Hohmann dip. But if they are in the orthogonal polarization, there will be no dip in theory. And we list the result of teleportation at other angles here. And we got visibilities of 84.9 for the best result here. Then we focus on, we can see here, we can see the count rate at different angles is, the difference is very big. So here we got 2000 count in 30 seconds, but if the angles was changed to another polarization, the coincidence will be decreased. This was mainly caused by the polarization dependency of the SSPD. So according to our test, in one direction, the SSPD have maximum efficiency, but in its orthogonal polarization, the efficiency is almost half of the maximum efficiency. Therefore, to solve this problem, we introduced the Faber polarization beam splitter. This is a product from Solabs. Such product have very high quality because it is used the Carl set prism here, and the extinction ratio is over 1,000 to 1. Then we talk about, we move to the entanglement swapping. Here we have source 1 in plus-minus state and source 2 also in plus-minus state. And if we have a coincidence between the detector 1 and detector 4, we know the plus state is detected. And it will hybrid the photons in channel 2 and channel 3 in an entangled state. But all the components in this setup is fibers. We don't know the polarization in the fibers. So we need to make a calibration first. To make the calibration, firstly, we insert 2 PBS here, and we make sure the photons, we rotate the polarizer half-wave plate, quarter-wave plate here, and we make sure the H photons from port 1 travels to port 8, and the H photons in channel 4 travels to port 7. Under this condition, so the H1 photons, after the operation of half-wave plate, quarter-wave plate, it is still in H polarization, but the H photons in 4 will be transferred to V polarization. Under this condition, the precise state will be transferred, will be exchanged with the phi state. So under this condition, we will detect this term, the precise plus state in channel 1-4, and the phi plus state in channel 2-3. Now we focus on this term. Oh, sorry. So firstly, we use a pump power of 80 milliwatt for source 1 and 85 milliwatt for source 2, and we got a visibility of 63 to 90% here. And to decrease the multiplier emission effect, we decreased the power to half, and we used 40 milliwatt. We found the visibility was improved from 63 to 68, and basically it was improved by 7%. And we confirmed this is this is the 5+ state. Now is the discussion part. We compare our coincidence count with the previous experiment. We found our coincidence about 100 count per second. This is almost 1,000. This is over 1,000 times higher than the previous result. So this was mainly contributed by the highly efficient source and our highly efficiency detectors. Then we compare our result with the previous best performance at 800 nanometer wavelengths. So the reference 1 and 2 is for the free space test of swapping and teleportation with over 100 kilometer. And the reference 3 and 4 is for the 8-photon entangled state generation. And we can see our count rate is comparable, and the visibility is also comparable. So for the future, our source can be used for the free space test of teleportation or entanglement swapping at a telecom wavelength. And also our source can be used for the multi-photon entangled state generation. And also maybe our source can be used for the future quantum repeater protocols. This maybe is very hard, but it is possible. Then I focus on the QKD application. Maybe our source can be used for the entanglement swapping based QKD. Such a scheme was proposed Such a scheme was proposed in 2011. And I think to demonstrate such a scheme, the lowest requirement should be have the 4-fold coincidence count rate should be not so low, maybe over 10 count per second. And all the visibilities in the entanglement swapping should over 71 to violate the Bell inequality. And compare with the decoy state QKD, which has been talked a lot in this conference. And the advantage is such a scheme will have a long distance, but the disadvantage is the count rate is very low. But I think it's still meaningful to demonstrate such entanglement swapping based QKD. Finally, I want to discuss about how to decrease the multiplier emission effect. So in our experiment, the multi-emission is still exists, and it will decrease our visibility. So recently, we demonstrate a scheme use the 10 gigahertz repetition rate cope laser. With such a high repetition rate, the average power per pulse is very low. Therefore, the multiplier emission is very low. And at the same time, a high repetition rate can keep a considerable count rate. So here is my conclusion. So in our setup, we use a group velocity matched PPKD crystal in a Sagnac loop as an entangled source, and we use highly efficient single photon detectors. And in the Hong-Mandel interference, we got red visibility of 73% and net visibility of 85%. And we got over 100 count per second in the 4-fold coincidence count rate. And for the teleportation, we got the maximum visibility of 84.9%. And for the entanglement swapping, we got 68 to 94% visibility. And for the future, our source can be used for the field test of entanglement swapping and teleportation. And our source also can be used for the 6-photon entangled state generation at a telecom wavelength. And it also has the potential to realize the quantum repeater or entanglement swapping based QKD. Thank you.
Question. I wasn't following when you described the background subtraction. does the subtraction itself take care of the multi-pair emission, or does it still remain in the net visibility measurement?
Yeah, maybe here. I think it's it's so low. Here. So yeah, this is only a roughly measurement. I think the multi-pair emission is still exist because if we decrease the pump power, we can see the background subtracted visibility still increase. So I think this is not the perfect way to subtract the background, but it is easy to do this in this way. Yeah.
Have you calculated that with your current full photon entanglement source and for the entanglement swiping based QKD? What's the distance you can achieve? How long you can achieve for the distance, and also the QCrypt? How you do the calculation?
No. We only consider to realize that we have not. Because our source now the visibility is not. Our visibility is not high enough. Cannot over. The raw visibility cannot over 71%.
Yeah. I think that's my question. Cause you can subtract the multi-photon pair noise by calculating the system, but you cannot do that when you are doing QKD, right?
Yeah. So I think it's still hard to realize the in terms of working with QKD. Yeah.